Welcoming Nick Bourdakos from IBM.
Hello, everyone. So today I'm going to be talking a little bit about object detection and how we can train our very own personal model. But before I talk about that, I want to talk a little bit about how computer vision kind of works and what computers actually see, just because I think it's extremely useful to have a little bit of an understanding of what's going on in order to train a model to the best that it can be. So to start, what do computers see? And this is probably something what the computer sees. It just looks like a lot of noise. And it's actually a picture of a cat. I just took all the pixels, and these are just the hex codes, so like FF83B7. And it just looks like a lot of noise. So how can we take this and turn it into something that a computer can actually understand? And what we can do is take advantage of AI and machine learning and deep learning. In order to train that, we need to show it pictures of different objects that we actually want it to identify. And we have to say, this is a dog, this is a cat. And we can't really just show it just one picture of a dog. We have to show it thousands, millions of pictures in order for it to start learning. And most state-of-the-art models, they are trained on millions and millions of images. But that's a lot of images. Like most of us, we're not going to have all those images to train a model. So we need to do something better. And a lot of you are probably thinking, I can look at an image one time and have a pretty good understanding of what that image is. We can look at it once. I can look at this Nestle Pure Life water bottle. And if you show me another one, I'll know that it's the same water bottle immediately. So let's play a little game. So I'm showing you this cat picture again. Really soak it in. This is a cat, okay? Now this one's a dog, all right? Does everybody know this is a dog now? Probably, yeah? Now, what about this one? Cat or dog? Dog? Okay. It was a cat. I'm so sorry. So, how can we learn so quickly? And I don't know about you guys, but I've been learning how to see for probably 20 years now. A little bit more, 24 years. What have we been learning all this time? Well, we start learning basic things like shapes. When the light hits our eyes, we don't just see this giant big noise that the computer is seeing. We actually see shapes, lines, curves, edges, all these various building blocks of vision. So when we look at this picture of a cat, we immediately know this is a cat. There's not even that much going on about it. It doesn't have its texture and it's blue, but we all know this is a cat, right? And we can tell that this is a dog. So we kind of learn all this just as we grow up. When we're babies, we start recognizing these basic patterns, and we're able to apply those patterns to actual novel objects like this Nestle water bottle. So when we do train AI on these millions of images, that's all the kinds of things that it's starting to learn. It starts learning edges, and those get put together and make up shapes and much more complicated objects. And we can use this. Once we train a model on these millions of images, we can take that model and teach it to learn new things. And when we teach it new things, we don't need to use nearly as many images. We can start with a basic of 10 images. And 10 images is still probably more than what we would need to identify something, but it's a good start. But what else have we learned, like going through all of these years of life? And we're going to play another game. So I'm going to show you a bunch of these pictures, and each one is associated with a label, A and B. So if we look at this first image, this is A. And this is B. And if I start going too fast, don't worry, at the end, I'll show you a recap of all the images. This is A. This is B. This one isn't A or B. And this one also isn't A or B. And then, so here's all the images again. What do you guys think that this question mark image is? Do you think it's A? Okay, 2 people, 3 people, 4. Okay, who thinks it's B? Okay, more. Everybody didn't vote though. Let's do that again. A. Okay. B. All right. It looks kind of split, but probably more B than A. It's also, this is A. So why is it A? It's partially my fault because I'm the one who decides if it's A or B. It might not be obvious that it's A, so it's my fault that I didn't do a good enough job of showing you all these images, or enough images. So the reason why it's A is because I was talking about the red circle in the middle. And A is a red circle, B is a yellow circle, and neither there's like a pink circle and a red square. So if I showed you like maybe 20, 30, I think it would be way more apparent which one was A or B. And that's because if I show you this, I'm going to show you a similar example that looks like this, but with actual objects. If I showed you this picture, most of you would probably be able to tell me that this last picture is an apple, right? It's pretty easy, and I think that's because there's a lot of context that we have. When we look at an image, we see this background, we can kind of throw that information away. We see the hand. Normally whenever somebody's holding something, we don't really care about the hand, we care about what's in their hand. And then so we're just left with this apple. But the computer, when it looks at these photos, it doesn't really, it doesn't pick that kind of information up. So that's why we have to show it a lot more images, because it needs to kind of realize that, oh, there's a lot of this like hand looking like object, it doesn't know it's a hand, but this object in all of the photos across A and B, so we can kind of just not use this information. This information isn't as useful as this apple, because this portion of the photo seems to be what is constant across A and B, but not in both of them. So we're finally at a point where we can show like 10 pictures, and we have a nice little cat and dog detector. So we show a picture, it tells us it's a cat, and great, it's working. And this is what we call classification. But today we're going to be talking about something different. So, and to illustrate like why we need something different is, what if we show you this picture? Is this a cat or a dog? There's both cats and dogs. So what we need is object detection. And what object detection gives us is the ability to detect dog and cat, both of them, and where they are in the photo. And this is way, way more useful because most of the times when we're taking pictures of things, there's like plenty of things going on in the photo. And with object detection, we can get a more holistic view of what's actually going on. And so we could even, this is only showing the head, but we could train it to show the entire dog and the cat. And if we see that there's a dog and then there's a cat above it, we could probably even say, oh, there's a cat on the dog. So we can build more complicated understandings of images instead of just cat, dog. And to train it, we just have to show the AI an image and where the dogs and where the cats are in the image. So in practice, we normally have 3 phases. There's the labeling phase, the training phase, and then when we actually use it. I'm going to be talking about cloud annotations is how we're going to label. Watson machine learning is how we're going to train. And then we're going to finally use CoreML to actually use the model. And before I go into showing you how to do all this, good training data is everything. As you saw, it can be very easy to accidentally not teach it well enough. It might be obvious to us that we're trying to say, this is an apple. But to the computer, you might need to hold its hand a little bit further. And here's some good rules of thumb when we go through this. And this might be very small. So the model that we originally trained on this millions and millions of images, it was trained on real-world objects. So whenever we want to take it a step further and train it on something else, it needs to be somewhat similar. You need to be able to take those concepts and pass it on. So it works well if it was trained on real-world objects and we show it this bottle and we want to train it on this bottle that it hasn't seen before because it looks similar to everything else. But if we wanted to teach it how to use X-rays and read X-rays, it doesn't look as similar. There's a lot more that it has to learn. So if we want an X-ray detector, we're going to have to go and train it on like millions of images of X-rays. And if we want to do like hand drawings, similar. Like the line drawings, they don't look very much like real-world objects. So we would need to train it on lots of images of hand drawing objects to get a better object detection. And again, it needs to be as close to your production environment as possible. So if you're using security camera footage and it's kind of like a dark, blurry image, you want to train it on dark and blurry things. You don't want to train it on like very pretty stock photos of people or whatever you're trying to detect, because it's not going to be able to connect the dots between those types of objects. And also, if it isn't very intelligent, even though it's called artificial intelligence. So when you want to train something, it works best on things that like a human can predict in a couple of seconds. So if I try to teach one of you something in a few seconds, that's the kind of thing that you want to teach it. So most of you could figure out that this is a Nestle water bottle, and then if I showed you this one, I could teach you that like fairly quickly. But again, with like things like medical images, like doctors have to go through like medical school. So this kind of technology doesn't work as well in that scenario, just because you need a lot more context and background to achieve that. And to get a good model, we want to train with at least 50 images. That'll give you like a fairly good model, but obviously the more the better. And if you provide thousands, it's going to probably be pretty well. And once you give thousands of images, you can probably start doing a little bit more of the out of context things like the hand drawing and scan documents and stuff like that. And then finally, I want to tell a little story. It's kind of like folklore sort of thing. Back in the Cold War, the US government was trying to build a classifier that classified US tanks and Russian tanks. And for some reason, we could only get photos of the Russian tanks at night. So we collected millions of photos of Russian tanks at night, and we collected photos of our tanks during the day. So then we trained this model, and we went into practice. We took some photos of the Russian tanks during the day, and some of our tanks in the night, or also in the night and day, but just a mix. And it was just random results were coming back. But what it turned out to be was it was really good at predicting if it was daytime or nighttime, but not very good at detecting the tanks. So you got to kind of think about like the little biases that were kind of accidentally teaching it. So it's good to have a variety of angles, backgrounds, just lots of different things, so it can actually learn what you're talking about and not something that you might not be thinking you're teaching it. And now I'm going to try and do a live demo. So this is the Cloud Annotations tool. And this is what a tool that I built to help me label images, and it's we're going to go over how to do this in a workshop tomorrow. So if you're interested, please stop by. So we can create a bucket. And then we're going to do localization, because that gives us the ability to do where the location of the objects are. And then we can just upload, here's a bunch of pictures of me holding beer, because we're doing like a happy hour kind of thing, and a beer detector. So let me find some good pictures. I don't know what beer this is. Okay, that's an Einstock. So we can give that a nice label. Another label. And I'm not going to bore you and label this entire thing. But with cloud annotations, it makes it easy. You upload a video, it splits it into frames, you upload a bunch of photos if you want, and it's all synced to an object storage bucket. So it's all in the cloud, and it makes it really easy to just draw all your annotations, it all gets synced to the bucket, and then that makes it actually really easy for us to train it later too. Another perk of it being on the cloud is that it makes it really easy to collaborate with people. So I will make a new tab. Okay. All right, so we have two of these open now. And as you see, there's a little person indicator way over here in the corner, because two people are looking at the bucket, and then if I draw some labels, they also show up in both places. So like you and some other people can also label images, because I know I don't want to label thousands of images, so it's useful that other people can. And I took advantage of my girlfriend because, oops, wrong bucket, AltConf beer. Yeah, we labeled 1,000 images together because that's a lot of images just to label by yourself. And then so once we have like all these images labeled, we can use something called CACLI. That stands for Cloud Annotations CLI. Here's the GitHub for it. And it's github.com/cloudannotations, and then the training repo. And so what CACLI does, we can continue to clutter my desktop and make dir emojis test. And then we can, if you just run CACLI train, it'll, I guess I already have it. Oops. CD emojis test. And if you run calculate train, it'll ask you your, behind the scenes, it's using Watson machine learning, like I said earlier, to actually train a model. So you can give it your Watson machine learning credentials, and then the object storage credentials that you use to log into the cloud annotation tool. And then it'll ask you to choose a bucket. So if we did the AltConf demo, then it would start training. I'm not going to train it, but I'll show you a example. So Cackley list. And then training time, it normally takes, it depends on how many steps you train. And I normally say to train it about 20 times the number of images that you are training it on. So for the beer one with 1,000 images, I would train it for 20,000 steps. And that would probably take a fairly long time to run it on your local computer, which is why we kind of use the Watson machine learning, because we can take advantage of high-end GPUs for free if you're using the light tier. So then we can actually train it like really fast. And most of the time, it only takes about a half an hour to train it with Watson machine learning. But again, it depends on how many images you use, how long you're training it for. So I'm going to go ahead and download this, the emoji one. So Cackley, download emoji. And then this is going to download a CoreML model, a TensorFlow.js model, and a TF-Lite model. So you could use it in the browser, on your iPhone, or on an Android phone. Cool. And then once I'm going to use the TensorFlow.js one, just because it'll probably be easier to show on my laptop. So I'm going to go ahead and download this. And then, yeah, as you see here, once we download it from Cackley, it gives us these 3 different model formats. And all we have to do is drag this into the project. And then let's npm install. And this will just install our dependencies. Yeah, and then so this emoji detector is, you can show it your hands, and it'll detect if it's this hand emoji, like a thumbs up or peace sign kind of thing. And we'll see how well it works in here. I didn't really train it in dim lighting, so you'll probably get to see it fail pretty nicely. While this is loading, does anybody have questions so far? Yeah.
So how to identify for unidentified object, UFO or alien?
How would you identify them?
Yeah.
You. Okay, yeah.
You have difficulty.
Here, do you want to ask the question again in the microphone?
Yeah, how to identify for unidentified flying object like a UFO or aliens?
Right. So.
Because they can change shape.
Right. So if you want to identify UFOs, you're going to need to get a lot of photos of UFOs, or maybe even fake photos that you think UFOs would look like. Any other questions? Yeah.
I just tried to ask them about each other.
Okay.
But my
Sorry.
question is, so yesterday,
Sorry.
if you looked at the keynote, they announced that you can do If you looked at the keynote yesterday, they announced that you can use CoreML to do like adaptive learning. So you can like adapt your model to like new images, new image sets. How do you think Watson can use that? Or because I think it's pretty much create ML based. So how would you like transfer that to like Watson's algorithms, or like is there a strategy? Do you think there are any ideas? How would that scale?
I don't know too much about the new adaptive learning stuff, so I'd have to look into it. But I feel like it could probably work. With Watson machine learning, you can train it with any kind of code that you want. So you don't have to. If you run calculate train, it's just using the models that I'm providing. But you can also run calculate train and then with your own training zip. So I'm sure it's definitely possible. Any other questions? Yeah.
I was wondering, is it necessary to always have the exact same number of images per label, or is it like, should it be just like roughly the same number?
It should be roughly the same. You don't want to have orders of magnitude, just because if you have like thousands of images of a bottle and then like 10 of something else, then it's probably going to be heavily leaning towards bottle all the time and not much the other one. Yeah.
Does the order of the images matter? Will it always produce the exact same model?
It won't always produce the exact same model. There's a lot of randomness involved in training. So every time you train, you'll always get something slightly different. So you might want to run it a couple times, and you might end up with better or worse results. But it normally comes to about the same kind of thing, but a lot of randomness.
Does the order matter?
Not really, no. Anybody else? Cool, I'll try to do this demo. npm start. Hope it works.
I should have.
No, you're fine.
Oh, yeah.
Oh man, I don't have the. Well, it's detecting my hands, but it's supposed to show emojis, but I forgot to hard code the emojis. But I'll tell you, it is working. It's not very fun, but let me see if I have the actual one. Yeah, here we go. Here's the emojis. All right, then. My computer is heating up furiously. It's loading. Oh, it's kind of working. I think they might be shifted, but it's doing things. Cool. All right, that's it. Thank you for coming. Any other last questions, or?
Right, can you?
Yeah.
Hello? Sorry, can you hold 1 second? We need to get all the questions on the recording.
Sorry.
So oftentimes you will get
bunch of images of the object, but of different size. Does that impact the training? How would you normalize that?
Yeah, so when you're training the model, it works really well with like translations. So you don't really need to have it in like every single position, but size does matter. So it's good to have a variety of very close, very far, that kind of stuff. Yeah, get like a good mix of close and far. Yeah. Wait for the mic.
Same question, but about rotations. Like, do you have to do the different rotated?
Yeah, it normally it works to some degree with sizing and distance from the camera and rotations, but you'll have a drop in confidence if you have them all vertical and then like you try it like upside down. But it normally does like still get it.
So when you have a normal, sorry, I'm talking. You have a normal set of models, like would you take and maybe just like, rotate them all just to give it the difference?
Yeah, so a common practice with computer vision training is having like a set of augmentations that you can run on the image. And that's like random cropping, so you could crop in closer to make it bigger, or also rotating images, changing the lighting intensity, different kinds of things like that. And it does help. Any other questions? Cool.
All right, everyone give a hand to Nick.